Alright, Assalamualaikum warahmatullahi wabarakatuh. Very good day to everyone. So today I'm going to discuss question number 1, which is taken from tutorial question for subtopic heat. And the question said that the steam pipe is covered with 1.50 cm thick insulating material of thermal conductivity 83.7 watt per meter per Kelvin. So over here we have a pipe, okay, a steam pipe, which is steam is flowing inside the pipe, and then it will be covered by an insulator, which is given the thermal conductivity as 83.7 watt per meter per Kelvin. Okay, so over here I'm going to put that is the thickness. Okay, that is the thickness of your insulator. The question asks how much energy lost every second. So how much energy lost every second per second, which means it will be equal to dq over dt. And the reason for that, because dq is heat energy and then over time, which means in second. Okay, when the steam is at 200 degrees Celsius, now we know that our steam is inside this very pipe, which means inside the pipe will be temperature of 200 degrees and the surrounding is 20 degrees Celsius. So over here is our surrounding. Okay, so here is our pipe and here is our surrounding. So which means inside the pipe will be 200 degrees and then the temperature is greater than 20 degrees, which means that will be T hot inside the pipe and then surrounding will be T cold. Okay, the reason why we need to know what is T hot and also T cold, because it will tell us the direction of your heat. So now our pipe has greater temperature compared to surrounding, so that's why our flow of the heat must be from the hot body to cold body, which is the direction will be in that direction. And of course it will goes with the other direction. So as you can see now, the thickness of your insulator is the same direction as your Q. Next, I'm going to apply the equation for dq over dt, which is given by K A dt over dx. So our K is already given. The area is not calculated yet. dt we have th minus tc, and then since our direction of q, our direction of heat is the same direction of thickness, which means our dx will be thickness t. Now it leaves us with area. Now how to find the area for this question? Now if you look at back, this is this insulator is covering our pipe, and we know that our pipe is in cylinder. The shape is cylinder. So which means now we're dealing with cylinder, and the cross-sectional area for cylinder, okay, that is your cylinder. That is the length of the cylinder, and then that will be the radius of the circle of the cylinder. Now to find the area or the cross-sectional area, it will be 2 pi r u times with L. So that is how you find the cross-sectional area for a cylinder. But the thing is, we don't know what is the radius. But in the question give us the circumference of the pipe, which is equal to 800 centimeter. Now circumference, circumference basically equal to 2 pi r, and then it said that it will be equal to 800 centimeter, which means 800 you times with 10 to the power of negative 2 meter. So over here I can substitute your area. So area is equal to 2 pi r, which is equal to 800 times with negative 2, and then the length is equal to 50 meter. So now we have all the infos. Okay, so we can move to the other slide to calculate what is the energy loss every second for this question number 1. So dq over dt is equal to K U times with area, and then dt over dx. So I'm going to write all the values, which is over here will be 2 pi RU times with L. That is the cross-sectional area of your cylinder. And then this will be T hot minus T cold. And then dx will be the thickness of your insulator. So this one is equal to 83.7 watt per meter per Kelvin. And then the area, cross-sectional area just now is equal to 800 times 10 to the power of negative 2 U times with 50 meter. And then your T hot is equal to 200 degrees Celsius. You minus with 20 degrees Celsius. And then the thickness of your insulator is equal to 1.50. Okay, convert into meter, which is times 10 to the power of negative 2, which give us dq over dt, or energy loss for every second, okay, by the steam is equal to 4.02 U times with 10 to the power of 8 joule per second. Or for this one, okay, the other unit is watt. Alright, next will be question number 3. I'm not going to discuss question number 2 because the step or the solution for question number 2 is already given in the example from your previous videos in lecture notes. So I'm just proceed to question number 3. So over here we have question number 3. It said that a bar of gold is in thermal contact with a bar of silver of the same length and area. So here in the middle we have two metals. The first one is the gold, and also the other one is silver. So I'm going to label as AU, and also here is the silver. Connecting two bodies apart, which is one is hot and one is cold. So on the far end of your gold, it said that the temperature is 80 degrees Celsius. So over here is 80 degrees Celsius, which is, we know that will be T hot. And then on the other hand, or the other part, is the cold body, which is the temperature is given as 30 degrees Celsius, and that will be T cold. Find the temperature at the junction when the energy flow reaches a steady state. Okay, now we're going to allow the heat to flow from your heat body here towards the cold body, and then the heat going to pass through these two metals. And then what would happen is, as the heat flow from the hot end to cold end over here, somehow it will reach a steady state, which is over here at the junction between these two metals. They will reach a temperature, and that temperature is the temperature that we're looking after in the question. And then for that, the equation will be dq over dt, the rate of heat flow for the first metal, is equal to dq over dt for the second metal, which is silver. Okay, so if I'm going to substitute number 1 and number 2 using these two respective metal, it will be thermal conductivity for gold, the area of the gold, and then it will be the change in temperature, which is the gold is connecting between two temperature, which is T at the junction and also the hot body. So it will be T hot minus T, not T cold, divided by the length of the gold. And then on the right side, it will be silver. So we have thermal conductivity of a silver, the area of the silver, and then the change in temperature, it will be T at the junction minus with T cold, which is 30 degree, and also divided by the length of the silver. Alright, so in the very first sentence of the question, it stated that these two metal, gold and silver, they share the same length and also the same area. So the length of the gold is equal to the length of the silver. So the length of the gold and also the length of the silver is equal or same, which means we can take them out, cancel out, and then also the same in area. So which means the area for the gold and also the silver also the same, which means we can take them out too, which is leave us with the remaining terms in the question. So we're going to proceed. So next it will be thermal conductivity of gold, and then the temperature difference, which is T hot minus with T junction, is equal to thermal conductivity of the silver, and then also the change in the temperature, which is equal to T at the junction minus with T cold. So KAU, or the thermal conductivity, is equal to 314 watt per meter per degree Celsius, somehow equal to 80 degrees Celsius minus with T, that is unknown, and then that will be 427, again T is unknown, minus with T cold, which is equal to 30 degrees Celsius. So to solve this, I'm going to use expansion. So our T is equal to 51.19 degrees Celsius. Okay, so that is the solution for question number 3. I think that's all for today for our session. Thank you very much for your attention. Again, Assalamualaikum warahmatullahi taala wabarakatuh.